Okay, guys, thank you for your patience regarding this video. Let's get it going. So DC voltmeters and ammeters are next after Kirchhoff's laws, and we use voltmeters to measure volts, of course, across a circuit segment. So we could say, oh, you know what, I want to measure the voltage drop across R2, or maybe I want to measure the voltage drop across R1, or maybe I want to learn about the EMF of this battery, and I want to measure that voltage as well. So here's what we do. This is a voltmeter. Okay, that's the symbol for it. This is an ammeter, which we'll get to in a second. The voltmeter will have leads, a positive lead. Let's do R2. And that one seems easy. And a negative lead. And we'll go like this. And or vice versa, positive, negative. However. And as we do that, then this voltmeter will tell us the voltage drop between this point and this point. Okay, so we can call this A and this B. And we'll get a certain measurement of V, A, B. Okay, an ammeter, if we want to measure the current that is going through this circuit, so this current there's some definite current going through, and it's, in order to do that measurement, what we have to do is break our circuit and insert the ammeter. So we cut the circuit and we run our wire to the ammeter and then back out of the ammeter. So a voltmeter is a parallel measurement. Parallel, and an ammeter is series, inline. Slash inline. Okay, so that's how these two things work. In the very fundamental rudimentary aspect, let me just say one thing real quick. No matter what happens, let's just use the voltmeter for example. So here we have current that's going this way, and we learned Kirchhoff's rules, right? And we know that there's a junction rule, and we know that for this thing to measure anything, it has to have a current that comes into the voltmeter and a current that goes out of the voltmeter. So this current is IV for voltmeter. This current is IV. And then that means that the voltage across the resistor, or the current across the resistor, IR, or let's call it I2, that is not the same current that was going around in the first place. So no matter what happens, when you do a measurement like this, and the same thing's true for the ammeter, even though I'll have to explain why in a minute, but no matter what happens, you're not truly getting an accurate measurement. We work hard to make sure that the measurements are accurate, and we do things to get it close. But no matter what happens, when we measure, aspects of a circuit, we are altering the circuit a little bit, okay? And we try to do it, we try to minimize that alteration, of course, but sometimes it's not easy to do. Okay, so here we have, I've got this, this is my galvanometer, okay? And this is what we're learning about, the two things that we're learning about. Our galvanometer, it'll do both, okay? So a galvanometer comes from Luigi Galvani. Is that it? Was that his name? Yeah, Luigi Galvani in the 1800s, who they also named galvanization after. He studied all this stuff too, of course, and a galvanometer is just a like a thermostat with a coiled spring inside, like that, and then as things happen to that coil, it moves the needle, right, from right to left. So it starts over here all the time. This is its basic point, and then it'll move all the way to its maximum point. And it's because this spring contracts or expands. Okay, so that's how a galvanometer basically works. I'm not going to tell you about how it works, actually. But this is how the needle works. Okay. At any rate, it'll go from this point to this point and max out. Okay, so we'll be talking about this. All right, this is mine, okay? And if we notice here, we can, I don't know if I can delete this or not. Yeah, let's just delete that one. You saw the probes, right? Okay, good. It has probes, and we can do whatnot with the probes, but okay, so here's our galvanometer, and if you notice here, I've got DC voltage, I've got AC voltage, I've got current milliamp in DC. I can go up to 250 milliamps. We can look at a battery, we can look at a 9-volt battery, and then we can look at button batteries. And since we've learned a little bit about batteries, we can see why there would be a selection of a 1.5 volt battery, which is a lot bigger than a little button battery. And that's because the amount of charge that a 1.5 volt battery will give up is a lot. It's like the truck battery compared to a motorcycle battery. A button battery would be the motorcycle battery because it's so much smaller. So that's why they have to have, you do different ones. Okay, so here's our galvanometer, and the needle is going to go like this. And if we are on a certain 250, let's say we're looking for DC voltages of 250, it'll max out right here at this 250 line. Okay. Great. So we're going to come back to this guy in a little bit as we're doing some of these things. This galvanometer has an internal resistance. Oh, sorry about that. Everybody's going to get seasick with me driving like this. Okay. It has an internal resistance that we're going to call RG. It also has a current sensitivity, which we're going to call IG. So RG is, well, let's do that. Boom, boom, boom. Internal resistance, and IG is the current sensitivity. I don't know if you guys can see on this guy, but right here and over here, there's a little dial that I can adjust and make it such that the ohms are 0. It basically turns the internal resistance to a point where it balances the ammeter. So it just changes, it alters the internal resistance. There are ways of creating dialable resistances, and that's on a dial, and you can do that. But for our sake, we're going to figure out what the internal resistance is. How are we going to do that? We're going to say, I don't know if you can see this, but the lowest thing that we can measure is a 1.5 volt. So if V equals IR, and we can measure a 1.5 volt thing, let's solve for our internal resistance. RG is equal to our V over I. Our most sensitive is 25 milliamps. Okay, so that's our current sensitivity. That equals 25 milliamps. We've got our voltage that we can do. The smallest voltage, if you notice on this thing, is the 1.5 volt button battery. So if we come down here and put our current sensitivity of 25 milliamps, then our RG is equal to 60 ohms. That's quite high, and I'm pretty sure that it's a lot less than that. Maybe closer to 10 ohms, but that's here nor there. We're going to use 60 ohms for all of our sensitivity on this. Okay, so we want to measure. Let's do a measurement first of a drop in voltage across a circuit, and here's what it's going to look like. So there's this circuit out there that we don't know a lot about. We know nothing. Okay. Okay, there's our circuit, and we have an R load here. And we suspect that it's approximately 200 volt drop. Okay, you kind of have to have a good idea of how many volts you're going to see dropping across the resistor to do our thing, because we're going, and it's a DC voltage. So if it's 200 volts, we're going to definitely we're going to select this right here. So we're going to take this dial knob and we're going to slide it over so that it points right here. Okay? And what that'll do is it'll put a certain resistance, a certain resistor in our circuit. And we're going to figure out what that resistor is. Okay, so let's draw the circuit first so you guys can see what's happening. So let's come down here. We're going to attach our lead, one lead here. And the first thing in our and so that's our lead. This is our galvanometer. Inside our galvanometer, we have switched to the 250 DC. We've got our galvanometer resistance. We've got some resistor R, which we don't know. We've got the actual galvanometer itself, okay, for G. And then we're attaching here to measure the voltage drop across this resistor. This right here is equivalent to this, okay? And you could call it a voltage galvanometer or whatever. But that's what we just drew, okay? That's the symbol. All right, so good. We are going to, we want to find out what this R is. So if we say that the R total is equal to our RG plus our R, and then that equals our V that we have selected. So we selected VG equals 250 volts. And our current is our IG. And we've already said that IG is equal to 2, I'll write it again, IG is equal to 25 milliamps. We can solve this equation for R, the big R, and we can find that that R is equal to our VG over IG minus RG. Okay, that turns out to be 250 over 25 milliamps minus our 60 ohms. What is R? What is that R? You guys probably have already done it by now. At any rate, it's 9,940 ohms. So 9,940 ohms is what got put in place, and it was probably not 940. Excuse me. It was probably 10,000 ohms. And that's just, it's so close to 10,000 that I can't imagine that they do something crazy just to put a little bit of to take a little bit off of it. I don't know. It's so big that RG is nothing compared to it. So it really, RG really doesn't factor in most of the time, okay? Sometimes it does on very sensitive situations, but... Okay, let's look at a galvanometer. That's a galvanometer as a voltmeter. We're going to now look at a galvanometer as a ammeter. Okay, so as an ammeter, let's draw a new circuit. And here we have our battery. It's going to come around over here. It's going to come up over here. And here's our load resistance. And then it's going to come back around like this. Okay, and there's our plus and minus. This is our R. Okay, we want to measure the current that is going through this, okay, going across all the circuits and their stuff. What do we do? Well, we're going to take and insert our ammeter, and the ammeter is going to look like this. It's going to split. It's going to have a top side that has the internal galvanometer resistance. It's going to have the actual dial itself, and then it's going to come down. And then over here, it's going to have another resistor that is called a shunt resistor. RS is equal to a shunt resistor. So that shunt resistor, set timer for 30 minutes. That shunt resistor needs to be smaller because, so we've got some current going through our loop. That current is going to hit here, this junction. It's going to split. It's going to go that way, and it's going to go that way. We're going to have one, I'm going to call it IG, that goes across the galvanometer. And then we're going to have another IS that goes across the shunt resistor. Where do these come from all the time? All right, so we know there's a junction rule thing that's going to come into play here. And this is our I load. So our I load is coming in there, and then IS is going down. Our IG is going up. So if we drew the close-up of that junction, here is our I load. That's our IS, and that's our IG. Okay. The path of least resistance is the RS, and we want it to go through the path of least resistance. So the shunt resistor needs to be smaller than our RG. And we know that IG has to equal 25 milliamps. So we're going to write that again, 25 milliamps. The I total, we're going to suspect that we're going to find a current of, so suspected current I load is around 150 milliamps. Okay, so let's go back up to our ammeter and look. If we're going to select something on here to do our current, we have to come into this range right in here, right? So we're going to be either putting the dial right here or putting the dial right here. But if we're suspecting that it's 150 milliamps, then we need to have something larger than 150 milliamps, okay? So 250 is the one that we're going to select. So 250 is our choice. So our I total, I don't like that. I total is 250 milliamps. That's going to be our maximum thing. So we're going to consider that as our load. If that ends up being our total load, then it'll give us a full galvanometer response, okay, all the way from one side to the other. All right. So we're going to use the junction rule. And we're going to say that IL is equal to IG plus IS. And we know IG. We don't know what IS is. So we solve for IS equals IL minus IG. I'm still not 100% here with my controls of this thing. Okay, so IS. IS then is equal to our IL, which is 250 milliamps. We suspect it's less than that, but we have to use the full, right, the full Monty. So we're doing that, and then we're going to subtract off our IG, which is 25 milliamps, and then that leaves us with 225 milliamps is our current through the shunt. So what does the resistance have to be? So we're going to do a loop rule, and we're going to do a little loop through here. Did I draw the loop correctly? It doesn't matter, right? You guys know that. So we don't care. I'm going to do that loop, and the loop rule is going to give me IG RG minus, actually plus, it's minus IGRG plus ISRS, and that equals 0. And we can easily write out then that ISRS is equal to IGRG, and solve that for our RS. So RS equals RG IG over IS, and we already know what all those things are. here we go. 25 milliamps. RG, I don't know if you guys remember what RG is, but that was 60, excuse me, dang it, 60 ohms. And IS then is 225 milliamps. So this is the resistance that we have to have in that, when we select that 250 milliamp selection, we are selecting this resistance inside as a shunt resistance. And all of that ends up giving us a 6.67 ohm shunt resistance. Okay? Good. Now, you can see that we can't alter without altering the circuit. We can't measure anything without altering the circuit. So any measurements that we get will be very close, okay? But there are approximations, and there's one last thing. It's not digital, right? A galvanometer is not digital. So let's erase our graffiti here. The galvanometer, when you go to read it, you're going to see the needle at some point, and how accurate is that reading anyway, right? All you know is your battery is still good, or it's questionable, or whatever, or you've got 2.3 ohms, you know? It doesn't have to be great anyway. As long as you're fairly close, you've got the right answer. And that's basically how the world works anyway, with friction and everything. It's impossible to get. Once you start to measure something, you're always interfering with whatever that thing is. When you take a test, you're trying to measure a person's knowledge. Just the fact that you're taking a test messes up things. Anytime you try to make a measurement, you're always messing up the system. Looking at wildlife or whatever, there's so many different ways to see that. Okay, so let's move on from that. And we're going to learn a little bit about RC circuits. So, RC circuits. Okay, an RC circuit has to have a voltage supply. It has to have an R, and it has to have a C. What's a C? A capacitor, right? So, resistance and capacitance are now a part of our circuit. Okay, we're going to combine them. It's what we've all been waiting for all these long lives. All right, let's draw one. We've got our E. We've got a switch. We've got our capacitor. And we've got our sweet resistor right there. Okay. We're going to do R for resistance. We'll put a plus Q here and a minus Q there. And we'll call this a battery. And negative. Okay. And then, of course, when that switch flips closed, current is allowed to flow. Okay? And so there's going to be a current. I dropped off the internal resistance of our battery I hope you guys don't mind. All right. So here's the thing. Initially, this capacitor has Q normally on it, plus and minus Q, but initially that Q is equal to 0. So Q initial is equal to 0 coulombs, okay? We flip the switch closed, and all we're going to get is a drop of voltage drop across the resistor. And then the capacitor will start charging, okay? But let's just think exactly when we flip the switch closed, right at that very moment. All it's doing is letting the charge build up, but no charge is there yet, so I flows freely throughout the whole thing. We have an I naught, okay? Our voltage across the capacitor is equal to Q over C, and that has to equal 0 initially, okay? Gradually, the charge is going to build up, okay? And as it does, it starts to become its own voltage source, okay? But what is happening? It's charging up, and it's positive Q here, negative Q there. Well, that's opposing this guy, right? So gradually, the current, so I naught is going to equal V equals IR, V equals IR. So I naught equals V, I don't want to write V, I want to write epsilon over R. Okay, that's our I naught initially. Gradually, our I final is going to be 0, right? Because this Q is gradually going to get to a point where it balances completely with the battery. This capacitor is going to balance with the battery, and no charge is going to flow anymore across that resistor. So our I final is going to be 0. At that point, our voltage across the capacitor is going to equal our battery. Okay? All right. So we're charging, technically, the capacitor. The initial current, we already talked about, I naught over R. I naught equals our voltage over R, our EMF over R. Let's just draw a little graph that does this. Okay, here's time. Here's 1, 2, 3, 4. And let's do 5 for good measure. Okay. Now here's the hard part. This is the battery's EMF, okay? What we've drawn in blue is the capacitor's voltage. also its EMF, if you want to think of it that way. And at this point, I don't know if I drew it quite correctly, but this is 0.632 of our battery's EMF. Okay, so here's the thing. At a certain time, this is our first one, T1, here's T2, T3, T4, and T5. It'll gradually, the charge Q is gradually going to increase, right? And it takes time. So it's increasing all the time, and that's making our voltage increase across the capacitor. And at certain steps along the way, we've denoted as these T1s, T2s, and T3s, they have an equality, okay? T1 happens to equal RC. And believe it or not, I don't know. I'm just supposed to tell you it. I'd like to prove it to you, but I can't. T2 actually is 2 RC, 3 RC, 4 RC, and 5 RC, and so forth, right? It'll keep going, never quite reaching 100%, and here's why. So calculus is involved, right, finding this equation, and I'm going to do the equation without proof because we just can't. So here's our EMF of the battery. The voltage, of course, is equal to a curve that's related to that EMF, and it's e to the minus time over RC. Okay? So 1 minus e to the minus time over RC. If we happen to be at t to the 5, we're at t equals 5 RC. So let's look at that. Our voltage, C, is equal to whatever our battery EMF is, 1 minus e to the minus 5 RC divided by RC leaves us with 5. So now all we have to do is a little math and figure out what that equals. So it's going to equal this times something. 1 minus e to the minus 5. All right, let's do it. Minus 5. 5 minus, enter e to that, and we're going to make it negative and add 1 to it. And that is 0.993. 0.993. We can write that a different way, 0.993 of EB. So you can see that we're almost there, right? I drew the drawing fairly good. We're almost up to EB at that point. And what is it for T1? Hopefully, we'll see that it's 0.632. I'm not even going to do the math. It's 0.632. So there goes the suspense and all that. It makes sense, okay, that all of this makes sense. However, there's one thing that I want to introduce to you, and that is the notion of tau. So tau is equal to RC. Tau is the time constant. Tau is the time constant for an RC circuit. Okay, how does this make sense? T equals RC. Well, let's think about it for a second. So, if the resistance goes up, oh man, maybe we should go back to our drawing. If this resistance goes up, the current is going to go down, okay? So, if the current goes down, the charging of the capacitor time goes up, okay? Because it takes longer for the charges to develop. So, let's say R goes up, I goes down, time of charge goes up. Okay, so that makes tau get bigger. And if the capacitance C goes up, that means Q goes up, and that means that you need more time. Time goes up, and therefore our tau goes up. So they're both directly proportional. Okay, time is directly proportional to the capacitance and to the resistance. So it totally makes sense, and we're going to leave it at that. Let's look at discharging. Okay, so now we're going to discharge the capacitor. So we've unhooked our capacitor. It's been charged up. It has a plus Q on it, maximum, and a minus Q on it, maximum. And it's going to get put onto some load resistance. There's going to be a switch involved, of course. Once we close the switch, we're going to get a current. And there's calculus involved with this as well, but the voltage of the capacitor is going to decline. It's going to go down. It's initially V0, but it's going to decline by e to the minus time over RC. So this equation is the discharging equation, and the graph looks like this. So here's VC. Definitely starts out here equal to that and gradually approaches 0. And that's as time marches on. At some point, it's going to be most of the way down, or whatever 0.632 of the way down, which leaves us 1 minus 0.632. What is that? 1.632 subtract 368. Okay, so this is 0.368 of the way to the bottom. Okay, and then it'll do another, every single time it does another RC. So that's the first RC. Here's the second RC. It'll drop another this much of where it was here. Okay, so this is the same fraction. It's an exponential thing. You guys get it, I hope. Okay. Good. So far, so good. We're making huge progress. I'm very happy about all of this. So flash photography is the example that is most used. So wait, before we continue, that's discharging. This equation here is charging, okay? So charging and discharging of a capacitor, okay? At any rate, those are the equations that work. You're going to need to know those. And we're going to do an example. One of the best examples is flash photography, okay? And what they do is you have a flash bulb, and it goes off shining light for a certain amount of time, also opening and closing your shutter. Then you have a brilliant light coming from the exact direction that it needs to, so that your shutter, the light reflects, and the shutter captures the image. So a flash bulb needs an RC current circuit to open and close the shutter, but more importantly, shine the flash bulb. Okay, so that's really what we're working with, is the flash bulb. To flash for the appropriate amount of time. All right, so we're going to take a picture of a bee. And we want to see the bee, we want to see the wings, we want to see everything like it was perfectly still, but it's in flight. So a bee beats its wings 230 times per second. That's a lot. The time for one flap is 4.13. If you invert that, that gives you 4.13 times 10 to the minus 3 seconds per flap. And we don't want just one flap, because let's look at the flap as a circle. It's going to go down one side, up the other, and we want to do this so that we select just a tiny sliver, right, of that flap. So let's say we want 1/100th of that time. Okay, so we really want a time equal to 4.13 times 10 to the minus 3 divided by 100, that means 10 to the minus 5. Okay, so that's our time. And we're going to set that equal to tau, and that equals some RC. Okay, so if we're given our resistance for the actual flash bulb, so the resistance of the bulb is equal to 7.5 ohms, then we know what the time is. We can solve for the capacitance. What capacitance do we need? We need the actual time, tau, over R. So we're going to put in 4.13 times 10 to the minus 5, and we're going to divide that by 7.5 ohms. And if you notice, well, we'll talk about that in a second. 4.13 times 10 to the minus 5 divided by 7.5. That gives us 5.5 microfarads. Nice. But what is going on? What's happening? What did we just do? We have units of seconds divided by ohms, and we ended up with a farad. 1 farad equals a second divided by an ohm. And that is no joke. And you can flip that all around and say that 1 second is equal to 1 farad times 1 ohm. And you can say that 1 ohm is equal to 1 second divided by 1 farad. So yes, the units actually work, and believe it or not, and there you go. Okay. So I just want to say a little bit about this. There was a Warren Commission report on the assassination of JFK in 1963. And high-speed photography back then was able to capture, before he was assassinated, they had done this at MIT. They captured a bullet hitting a apple, okay? And they showed everything that was happening. And the Warren Commission report that happened in 1963 used the Zapruder film and found that there was 3 bullets shot. One of them was not deadly to the president, or they think he would have survived it. The other, however, was deadly and was just the 1 bullet that killed him. And because of that photography and the way that how quickly everything went down, they were able to determine that. And that's actually in the textbook. That's where I got it from. So that was pretty interesting. I'm sorry this video is going to go on for a little bit more, but you can pause and rest and do all that stuff, and I'm okay. I don't mind. But we're going to go a little bit further and talk about timing for RC circuits, because if you notice, this is a nice way to get something to do something at a certain time. So you can make an RC circuit work for timing. So things will happen automatically. And there are things that do it all the time. Your wiper blades, intermittent wiper blades on your car windshield. It'll wipe every time the circuit goes off. Flashing LED lights or strobe lights. strobe lights, pacemakers. All those things work really well because of tau equals RC. All right, so let's talk a little bit about a flash bulb light. Okay, we're gonna stick with an easy one. Let's look at what happens in a flash bulb light. We've got our EMF here. We've got a switch. We definitely have a capacitor. Gotta have it. We've got our resistor. Boom, 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 boom. Man, I'm smooth. It's like a kid who really doesn't know how to control their hand movements and do zigzag sawtooth Charlie Brown shirt. Okay. Then there's a load, and the load is a high resistance flash bulb. Okay, so high R load flash bulb. All right. First, what's going to happen? This guy's high resistance. That resistor's low resistance. There's going to be some current that's going to go through once we close the switch. Okay. All that's going to do is charge up this Q plus and Q minus. Okay. The flash bulb isn't going to work. It has a VL equals RL IL. And the VL has to get to a certain point before it'll work. Okay? So VL has to be 19/10 of our EMF that we are putting on it. That means it's almost 2 times. It's 1.9 EMF. So it's not quite 2 times, but it's 1 time. Or almost 2 times. It's definitely more than 1. And that means that once this capacitor, it rises up so that its voltage capacitor, goes up to the point where it's almost equal to the supplied battery EMF, then the total voltage will be 2 times that. And then once it gets close to being equal, then that flash bulb will go off. So here's a picture of the graph of the voltage, VC, we've got two of our EMFs. First, what's going to happen, we're going to close the switch. The switch is going to go up like this. It's going to get to 1.9 EMF, and then it's going to discharge, and some of the current is going to go away. It's going to drop back down for a little bit, and then it'll start climbing again, and it'll get up there, and then it'll drop back down, and then it'll climb, and then it'll go back down, and it'll climb, and it'll go back down. And this is the amount of time that the high resistance flash bulb will go off. So every time it hits this 1.9 volt situation, that flash bulb goes off, and it resets itself and starts right back up again. So that's it going off. Then it says, oh, well, I need to keep charging back up. It does. It goes off. So this is where it's bright, right there. And anyway, you guys get the picture. So that's it for today's lecture. Thank you. And I'm going to address all the questions about the homeworks right now.